We've just seen an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular to deal with something that you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.000000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with a decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. Okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it. So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left when I divide by 2. If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right. That is, x double divide by 2 is now 1 times 2 to the 3rd rather than 2 to the 4th, plus 0 times 2 squared rather than 2 to the 3rd, plus 0 times 2 to the 1 rather than 2 squared, plus 1 times 2 to the 0 rather than 2 to the 1. Or another way of saying it is, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit. And when I'm done with all of that, I've converted to binary form. So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that. All right? If the number's less than 0, I'm going to put on a flag that says it's negative, and I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, it's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in, because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example. If I start off with number as 3, and I do that computation, it didn't print anything, but the result is sitting in result, and there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was, in fact, what I claimed it was. So if I make it 19 and I run it and I look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1, plus 7 times 10 to the minus 2 plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to play. If I can find a power of 2 big enough to convert all of that into a whole number, that is, multiply it by something so that it gets converted into a whole number, then I can convert that into binary. I just did that. I know how to do that. And then when I'm done, just divide by that same power of 2, and I've got a representation in binary of the fractional part of this number. In this case, I picked an easy example, 0.375. If I multiply it by 2 to the third, or 8, that's going to give me out 3 in decimal. I can then use what I just did as my trick to convert that to binary. That's 1, 1. And then I divide by 2 to the third, which simply says shift it right 3 points. And there is the binary representation of that decimal fraction. That's cool, right? It's a really neat idea. What am I doing? I'm using something I did for one computation, but converting another problem into the same problem. In this case, given a fraction, I'm saying find a power 2 that shifts it into an integer, use the same machinery, and then shift it back. And I'm simply taking advantage of powers of 2 because that's simply moving the placeholder, if you like, for the decimal point, or I should say the binary point, in a binary representation. All right, there's code that'll do it. I'm not going to walk through it. I'm going to let you look at it. I'm simply going to show you that this will actually convert a decimal to a binary fraction. So if I take this and I run it, in this case it says give me a decimal between 0 and 1. Let's pick out a nice example. Let's start with the one that we had, which was 0.375. Sorry, let me make sure I'm here. And it says, oh, I'm going to tell you when I've gotten through it to get it up to something that is big enough, how many times I have to shift it over, what's the remainder, and there's the printed solution. Let's be daring and try another example I haven't tried before, just to make sure that it actually works. So again, we're going to call this out. It says, give me a number between 0 and 1. And I don't know, let's take 0.333. And what do I get? Well, it goes through a whole lot more computation. It's telling me what the remainders are, but it's running through that computation, and it says the binary representation for 0.333 is this horrible looking mess you see on my computer screen down there. But the point of this is, now I can take any floating point number, convert it into something that can be represented inside of the machine in binary form, and use it. And that, by the way, is why you will occasionally see these strange things where you're expecting 3.0 back, and it has a little bit of an extra piece on it because in binary, it can get close to it, but not quite to the place it would like. But with that, we now have a way of understanding how we can represent floating point numbers inside a machine where everything is stored just in terms of binary bits. What are some of the implications of this? If there is no integer p, such that a power of 2 multiplied by x gives me a whole number, then the best I'm going to get is an internal representation that's close, which is why I won't get something exactly right. And obviously, I'm only going to do this so many times before I run out of powers of p to use this. It also suggests that when you want to test equality of floats, you should be careful. You really don't want to given two floats x and y, you really don't want to use double equal sign because it's going to check to see, is the binary representation exactly the same? It might not be. It might be really close. So we're always better off using the absolute value of the difference of two floating point numbers. Is it smaller than some small number, rather than using the more exact, are they exactly the same? And then finally, as I've already said, we may not always get an exact representation for a float in the way we would like, but if I do print of something, why does it always return what I'd expect, even if the representation isn't different? And the answer is because wonderfully the designers of Python designed it so that it would automatically round to the closest representation in terms of that floating point number. But there are floats. Now we got ability to do integers and floats. We're in good shape.